Hi friends, this is lecture number 28.2. Today we are going to start parameter calculation of one phase full wave semi-controlled symmetrical rectifier with RL or RLE load, and freewheeling diode is connected parallel to the load. So these are the waveforms which we have derived in my previous lecture. So in these waveforms, see the waveform of thyristor voltage VT1. Here thyristor is reverse bias for a period of pi minus alpha. So we can say that circuit turn off time of this circuit is pi minus alpha by omega. Now see the waveform of output voltage. We get output voltage, that is Vm sin omega t, from alpha to pi. So V naught average will be 1 upon pi integration alpha to pi Vm sin omega t d omega t, because time period of this waveform is pi. So on solving this, we get Vm upon pi 1 plus cos alpha. So V naught average is equals to Vm upon pi 1 plus cos alpha, and we know that maximum negative value of cos alpha is minus 1. That's why V naught average will always be positive. So the operation of this this rectified circuit is one quadrant operation. Similarly, we can calculate V naught RMS, that will be equals to under root of 1 upon pi integration alpha to pi Vm sin omega t whole square d omega t. Now see, the output current I naught is constant. That's why average value of output current is equals to RMS value of output current, and that will be equals to I naught. Now we see that thyristor current IT1 is from alpha to pi. Okay, we get IT1 from alpha to pi, and the time period of this thyristor current is 2 pi. So we can write average thyristor current as its conduction period upon total time period into I naught. So average value of thyristor current is pi minus alpha upon 2 pi into I naught. Similarly, we can write ITRMS. For ITRMS, just take square root of pi minus alpha upon 2 pi of average value. So you will get RMS value of thyristor current. So RMS value of thyristor current will be pi minus alpha upon 2 pi under root of whole into I naught. So this is the shortcut method for rectangular waveforms, and this has already been told to you in my previous videos. Similarly, diode current, we see that from waveform, diode conducts from alpha to pi. Okay, and time period of diode current is 2 pi. So we can write average value of diode current as pi minus alpha upon 2 pi into I naught. For RMS value of diode current, simply take under root of this pi minus alpha upon 2 pi in average. You will get the RMS value of diode current. So RMS of value of diode current is under root of pi minus alpha upon 2 pi into I naught. Now see the waveform of freewheeling diode. It is also rectangular and it has time period of 2 pi, and we can see that we get diode current from 0 to for time period of 2 alpha. This is first alpha and this is second alpha. So we get freewheeling diode current for a period of 2 alpha during total time period 2 pi. So we can directly write average value of freewheeling diode current is equals to 2 alpha upon total time period, that is 2 pi into I naught. Similarly, we can write RMS value of freewheeling diode current as under root of 2 alpha upon 2 pi into I naught. Now see, during period 2 pi, we get plus I naught for period pi minus alpha and minus I naught for period of pi minus alpha. So average value of source current is equals to 0, while RMS value will be equals to, see, for RMS value we have to square the rectangular waveform. Okay, so on square this negative side waveform, that is for period pi minus alpha and its value is minus I naught, it will also become positive. So we can write RMS value directly as pi minus alpha upon 2 pi minus alpha upon 2 pi whole square of this, and take under root of this and multiply it by I naught. So we get under root of pi minus alpha upon pi into I naught. So these are all the shortcuts. Okay, and these shortcuts are only applicable when waveform is rectangular in nature. So CIS, so source current IS is non-sinusoidal in nature, and we can express any non-sinusoidal waveform using Fourier series, and Fourier series of this waveform has already been told to you in my previous lecture. So Fourier series expression of source current Is will be equals to sigma n is equals to 1, 3, 5, 7 etc to infinity 4 I naught by pi in bracket cos alpha n by 2 cos n alpha by 2 into sin n omega t minus n alpha by 2. So fundamental component of this current Is is, see, in this total expression, this 4 I naught upon pi cos n alpha by 2 is constant, okay? And for fundamental component, we have to put n is equals to 1. So when we put n is equals to 1, we get fundamental component. So fundamental component will be equals to 4 I naught upon pi cos alpha by 2 sin omega t minus alpha by 2. So this is the fundamental component. Now you can see that source voltage is Vm sin omega t, okay? Source voltage is Vm sin omega t. If we compare it with source voltage, then we can see that phase difference between fundamental component of source current and source voltage Vs is alpha by 2. So we can say that fundamental displacement factor is equals to cosine of angle between fundamental component of source current and source voltage, and angle between fundamental component of source current and voltage is alpha by 2. So cosine of this angle is cos alpha by 2. So fundamental displacement factor will be equals to cos alpha by 2. Now distortion factor G. Distortion factor G is RMS value of fundamental component of current upon RMS value of source component. Now what is RMS value of fundamental component? See, in this fundamental component, this 4 I naught upon pi cos alpha by 2 is the constant which is maximum value of this source current, and it is equals to IS1 max. And what is RMS value? That is equals to IS1 max upon root 2. So we can write IS1 RMS is equals to 4 I naught upon pi cos alpha by 2 divided whole by root 2. And what is RMS value of source current? This has already been told to you in previous points. That is equals to I naught under root of pi minus alpha upon pi. So on solving this, we get 2 root 2 cos alpha by 2 under root of pi in bracket pi minus alpha. Now what is input power factor cos phi? So for input power factor cos phi, you simply multiply the distortion factor with fundamental displacement factor. So on multiplying this, we get 2 root 2 cos alpha by 2 whole square and divided by under root of pi minus alpha. So this is the expression for power factor. Now this input power factor can also be found by equating input power is equals to output power. This we have done in our last video. So when we put input power is equals to output power, means Vs Is cos phi is equals to V naught average into I naught average. Okay, if we equate these two, then we get power factor cos phi. And what is Vs RMS? That is equals to Vm by root 2. And what is Is RMS? That is equals to I naught under root of pi minus alpha upon pi. And what is V naught average? V naught average is equals to Vm upon pi 1 plus cos alpha, and I naught average is equals to I naught. So simply put all these terms in the equation Vs Is cos phi is equals to V naught average into I naught average. On putting all these terms, you will get the power factor. So these are the two methods to calculate the power factor. You can calculate by any of these methods. And this one is using Fourier series. This is a bit complicated, but if you find it complicated, then you can simply calculate the power factor by using the expression input power is equals to output power. So this is all about this video. I hope you like this video. Thank you. Jai Shri Ram.